This is chapter 4, database design using normalization. We talked about the principles of normalization in the last chapter, but they were somewhat theoretical, and this chapter kind of takes it to the next level and says, this is how you put those principles into practice. At least that's the way I interpret this chapter. Luckily, it's a short chapter, so that definitely improves its digestibility. So what's the purpose of this? It's applying normalization theory to real databases. So look at some practical ways of solving normalization kind of problems, database design problems in databases. The premise of this chapter is basically that you're a database architect and you have received one or more tables of existing data. And your job is to figure out, how should this data be stored? Should we keep it in the current format, or should we change it in some way? Should we make it more normal by separating out tables and creating foreign keys, all that stuff we learned in the last chapter? Or is it okay like it is? Right, so that's the basic question that all these slides come back to is, should we transform the data for storage or keep it like it is? The first thing that we're going to do to answer that question is to assess the table structure, or the structure of the tables that we've been given. So we've been given this mountain of data, let's say, in the form of these tables. What's the best way to structure them for this new analysis that we're going to use them for, or this new system? This would be a little overwhelming at first. What does this data look like? What are the rows? What are the columns? How much data do we have? What are the different tables, and how are they connected? Yeah? So that's what this first assess the structure is about, is answering those questions. We want to see the lay of the land. Perhaps we want to see how bad or how good the existing database design is for this purpose. The first thing that the author recommends is to count the rows. The idea here is it'd be kind of useful to know how much data are we really dealing with. And there's some simple SQL to do that. You know this already. If we do count star as num rows from whatever the table name is, we will get back, right, a number aggregating how many total rows there are in each table. That will give us some insight into how big this thing is. Secondly, we should examine the columns. We'd like to know the number and the type of the columns. We'd like to know generally what the data looks like within those columns. And the SQL that the author shows here is useful for this. I don't know, has anybody used this top command before? It's pretty simple. It just says, give me the top, and then whatever number you put in parentheses, give me the top 10 rows. So just slice off 10 rows off the top of this data set and show me just those 10, not all of them. So this way you get all the columns, because you said star, but only the top 10 rows. Yeah? Next, we want to understand relationships. So we're going to determine dependencies and also keys within our data. We want to know those dependencies that we talked about in chapter 3. We want to know what functional dependencies exist in the data, what multi-value dependencies exist, and then using that information, we could determine what the candidate keys may be, what the primary keys may be or are already, what are the foreign keys, and how are things linked together. For this, to extract this information, we could look at the data. We might also have to talk to the users, the employees or whatever of the current system, who know about these deeper relationships than we could extract by just looking at the data, right? We have to interview some users to figure out, is there only one of these for every one of these? Can there be more than one of these for one of these entities? You follow me? So that may be some business logic that you can't decipher just by looking at the data, or you don't want to. It'd be much slower than talking to somebody and understanding how things connect. So we want to understand relationships in addition to data types and columns and rows. Next, we want to analyze the validity of the referential integrity constraints. Remember, referential integrity is just the statement that foreign keys have to exist, right? Values that are in as foreign keys actually have to be a primary key somewhere else. And in order to facilitate this in an automated way, the author points out some pretty cool SQL. It's a subquery, nested select statement, to easily answer the question, are there any foreign keys that violate the referential integrity constraint? And this is his data. This is his query. So he selects from two tables from SKU data. Well, he selects from SKU data the buyer where SKU data.buyer is equal to buyer.buyer. So you see he's kind of doing a join, making sure that in the two tables where buyer appears, it's finding where they're equal. And then on this outside select, he selects buyer from SKU data where the buyer is not in this inner list. Does that make sense? This is elegant. So you run this query and it'll show you, what do you want to get back from this? You want to get back nothing, because if you get back nothing, that means everything that is a foreign key is also in a primary key. If you get back something, then that means that there are foreign keys that don't exist in the primary key table. That make sense? So this is a good trick to have up your sleeve when you are doing this process of validating referential integrity. The next big question we have to ask is, what kind of database do we have? And he introduces a new kind of database that we haven't really considered before. The first one is an updatable database, this is the world we've been living in. We have this database and we're going to add and remove data from it. And because of that, we want to make sure that there are no anomalies on modification. Remember the modification anomalies we talked about in chapter 3? Right? All those are in the context of an updatable database. If we have an updatable database, we normally want the tables in B, C, and F so that we have eliminated those anomalies. Right? They can't happen because of the way we've structured the database. We got all those tables with foreign keys and primary keys that link up. Right? But if we have a database that's a read-only database, so we've just got this file that is going to be read and analyzed, perhaps to create reports or some other kind of data analysis. In that case, we have a different objective, right? There's no way that modification anomalies can happen because we're never modifying the database. Yeah. So in that case, we might want to be less normalized because we'd rather have speed than reduce all redundancy and modification anomalies, because our usage is one in which we never change it. Does that make sense? So if it's a read-only database, then we may not want to use B, C, and F and normalize that much. First, we're going to consider designing updatable databases. So what are the rules, principles we follow for updatable databases? And generally, they're all the normalization rules that we looked at before. Remember normalization? He reminds us here of some advantages and disadvantages of normalization. On the advantages side, right, normalization eliminates modification anomalies. Insert, delete, update. It reduces duplicated data, and that may help eliminate data integrity problems. And it certainly saves space as well. If we don't have to have the same string repeated 14 bajillion times, right, in all the different rows that is the SKU description of the same product that's been sold 14 bajillion times, right, we could eliminate that storage requirement. There are some disadvantages to normalization as well that we didn't consider as strongly last time. It's going to take more complicated SQL statements, right? We've got to do joins and subqueries to link together information from different tables to maybe get all the information that we actually want, right? Because it's spread apart into separate tables. And that's going to result in slower applications because the database has to do more work to get that data. It's got to do the joins. Yeah. For an updatable database, we take that trade-off, right? And because we would rather eliminate modification anomalies, and we'll take the hit on performance. You can see here, we're going to come back to this same slide on the other side and say if it's a read-only database, then it's not worth the trade-off. Yeah, we'd rather just have the speed because we don't have modification anomalies. Yeah. So here's his example. We've got this non-normalized table. equipment repair. You see it's got information about items, and it also has information about repairs done to those items. So if we wanted to normalize that, we would separate it out into an items table and a repair table. And they're linked together on the item number, foreign key, primary key. Does that make sense? Basically just what we talked about in the last chapter. This is how we split out a table and remove functional dependencies and put them in their own table. Now you see the redundancies that are in here, right? That they in equipment repair, there are several item number 100s. There are several things called drill press on the equipment type. Yeah, it's redundant, and we would have modification anomalies within that table. But by separating it into equipment item and repair, we eliminate that. Yeah? So next we see practically how do we split this? How do we do this normalization? And he's got a new SQL statement that shouldn't be shocking to us, but it is the first time we've seen an insert statement. So this is an insert statement. Inserts allow you to add new rows to a table, but in this case we're inserting the result of another SQL statement, a select statement. So this, again, you can imagine reading from the inside out. We select distinct item numbers, equipment types, and acquisition costs. So we're kind of stripping out the item information in that select query, and that's from the equipment repair, the big table, and we're inserting that into this equipment item table. So this is a way that you can put a select statement inside an insert statement to copy data from one table to a new table or an existing table. Does this make sense? Yeah? And actually, then we have to do it again to extract the repair information from equipment repair and put it into repair. Does that make sense? Okay, so that brings us to this question that we've already hinted all around. Should we always take our database to BCNF? And you know, whenever anybody says always, you need to be skeptical, right? Because that's a really strong word. And no, there are times when we don't want to go to BCNF. We've already looked at the idea of the updatable database. We probably don't want to go to BCNF to that level of normalization. But the authors present a classic example, they say, of a time when I think even in an updatable database, there is a functional dependency that we leave in, and that is the zip code. You know, if you know the zip code, then you can certainly determine the state, and you can probably determine the city and the state. However, zip codes almost never change. So because they almost never change, the likelihood of having a modification anomaly on that field is incredibly rare. And the authors say that any anomalies are likely to be caught by normal business practices. So instead of separating out the zip code and the city-state into a different table so that that determinant is, you know, moved out to a different table, and then having to join that every time you want address information, we would sort of we would denormalize it, right, and just keep zip, city-state zip all in one row in one table. Does that make sense? So there are times when we don't want to be super hardcore about being normalized, and zip code is one example. The other big example is when we're designing read-only databases. So these are non-operational databases where data has been extracted, and it's probably going to be used for querying or reporting or data mining kinds of applications. Since they're never updated, that is in the operational sense where we're adding rows and modifying rows, it may be that we import new data and add on to the bottom as new data becomes available. But since they're never updated, we want to use them differently, design them differently. So we saw this slide before. You remember the benefits and disadvantages of normalization. When we're in an when we're in a read-only database context, then we kind of want to swap these, right? That we would, we're not going to have modification anomalies, and we would like this to be as fast as possible, right? So the speed thing is where we would make up our trade-off, and we'd rather it be faster. So in this case, we might want to join multiple tables that have been normalized into one big monster table that has a lot of redundant information, but is much faster to query. So here's the book's example of that. Imagine we have these three tables: student, activity, and payment. We're going to do some data mining on this to see what students are playing the most golf, maybe. And to do that, we can basically run a join on those and join them all back together into one big table. You can imagine the SQL to write that, but we're not just writing the SQL once and querying it. We're creating a new table that is all of that data merged back together. And you'll see there's redundancy in that, right? Because you've got the same student ID multiple times, the student name multiple times. But that's okay, because we're not going to change this table. We're not going to update it. So this is denormalizing. And if you want to see how that's done, this is a SQL statement that does it. It's really not shocking that we could do another insert into statement where we've created this new table that's all three names pushed together, and we're joining them together. We're creating one query that joins all those tables together in the ways that they were linked before on their primary key foreign keys. So I think this whole chapter brings us a little bit more in perspective of normalization isn't the end-all be-all of database design, because sometimes there are times when those ideals are not what we want for our application of the database, in the data mining, or if it's an application that it's a read-only database, then the rules change because the usage changed. As we wrap up this chapter, the author points out 4 common design problems that are very practical, I'd say. First is the multi-value, multi-column problem. So we're going to look at each of these and then talk about how to address them. Secondly is the idea of inconsistent values in rows. Thirdly, what do we do when we have missing values or nulls in the data? And lastly, what do you do when you've got this general purpose remarks, notes, comments column? So first, the multi-value, multi-column problem. I'll sum this up by just saying it's when you have the same basic attribute, but it exists several times. So it's in several columns of a table. So for example, if I have this employee that has normal stuff like last name and, sorry, that should be first name and last name, email, and then they have 3 auto license numbers, an auto 1 license number, auto 2, auto 3. When you see junk like this, right, you should begin to think, that's not the best way to structure this database. When you see auto 1, auto 2, auto 3, right? We're basically putting multiple different values in as different columns. And it's really another form of the multi-value dependency. We don't want to do this. The solution is what? It's what we've seen before. What should we do to fix this problem? Take out those 3 and put them in their own table that will be linked back to this employee, where an employee can have one or many automobiles, right? We'll have different license plates. So it's just like we saw before, using 4th normal form to solve multi-value dependencies. We just need a separate table. Next problem is, well, what do we do with inconsistent values? That just means we have slightly different forms of the same data. And the book has 2 good examples of this. Imagine we've got this description of the items: corn, comma, large can, comma, corn, comma, large, and large can, corn. You see the thing, those are clearly like 3 ways of saying the exact same thing, and we probably don't want all 3 in our database. So this is just different ways of coding the same information. Another example would be just people misspell stuff. So in this case, we would probably, if we want to have a cleaner database, want to clean this up and replace them all with one standard version so that we can actually count and see how many times coffee is used and have a real number when we do our data mining or our analysis. One way to fix this is by using SQL, right, and the group by clause to help us find when these things are different. The authors say that primary key, foreign key values are particularly problematic on this, that if we've got multiple values, inconsistent values that are the foreign key or primary key, right, that's going to cause some issues, and they're not going to be linked correctly. And in order to detect that, to detect this issue with their referential integrity constraint, we could use that SQL that we saw before, or we could also use this SQL here that we're going to count SKU descriptions, grouping them by SKU description, so that'll kind of aggregate them by every unique SKU description. Does that make sense? Since we're grouping by SKU description, we will get something where every unique SKU description will be on its own row, and then the count, which is called name count, for each unique one of those will be out to the side. So this is what the data would look like. And we might, as you see how this, by smashing all that down into a single column for every one, would show us if there is some weird duplication. So we could run this SQL group by clause on suspected columns where we think there may be some inconsistent values. Third problem is when we have missing values, when there are nulls in the database, that can mean different things, and we'd like to know what thing it means. Null values are ambiguous. They might indicate that the value is inappropriate. So his example, taking it back to the realm of biology, right, which we like, is the date that you last had a child. So the date of last childbirth. For men in your database, that's just inappropriate, and it should be null, right? Like null is the correct value to be in that. Yes. However, it may be that the value is appropriate but unknown. So if we have null for a woman, does that mean that she's never had a baby, or that we just don't know the last time she had a baby? Yeah. Or it may indicate that we know that she had a baby, we just never got around to entering it. You know what I'm saying? So there's that ambiguity. Ambiguity's bad. What does the null mean? All right, how would we interpret that? If we're trying to do a count on what percentage of the women in our database have had a baby in the last year, and we said nulls mean that she didn't have a baby, then we couldn't really trust our results, because it might just mean it wasn't entered or whatnot. Anyway, so we need to deal with that. And he does show you this bit of SQL. The keyword is null is on the end. So this is a way to run some SQL and find out if there is the null value in any of the cells. And in that case, you can begin to do some error checking on this. Yeah. And figure out how you need to handle this. Now, handling it may be a pain, right? If we actually have to go back and say, all right, I've got nulls for all these women. I need you, clinic, to figure out if these women actually had babies, they weren't entered, or they just didn't have babies. And right, you see how hairy that would get. That wouldn't be fun. All right. Last problem is the general purpose remarks column. This is comments, notes, remarks that people may have made, and they just put it in this big blah text field at the end because there wasn't any other good place to put it in the form. Now the thing about this is you might be tempted to say, all right, well, it's just remarks, it's just notes, throw it away. It doesn't fit inside a structured database. Problem is, they may contain really, really valuable information for the business usage, or even to your data analysis. So just because the data is stored in an inconsistent, verbose, maybe very verbal way, the column may contain many different data items all thrown in there together. It may be used inconsistently. It may be empty on 3/4 of your data. You might be tempted to throw it away and not look at it because it's going to be much harder to analyze in an automated way, right? Because you don't know the structure of it. However, really the best solution is to identify the purpose of this column and then create new columns for each purpose, extract the bits of information from it, and put them in the appropriate columns. The only problem with that is it would take forever, right? It would be very non-automatable, and you'd probably require somebody sitting and reading it and manually moving stuff to different columns. That would not be fun. All right, so to sum this up, we are looking at, in this chapter, how do we do database design using the principles of normalization, but practically. And generally, we have seen through a little bit of additional SQL trickery how we could check for common design problems and how we can actually kind of trade off normalization versus denormalization depending on if our database is updatable or read-only. So what we learned in this chapter was how to solve practical problems related to normalization or not, right? If we don't need normalization because it's a non-updatable, a read-only database, then forget about normalization and just put everything in one big table because that is going to be faster for us. So this is chapter 4,